Hey there, everybody. Welcome back. We're going to start 13.4 for calculus. This is on the differentiability of multivariable functions. So let's just jump right into it. Recall that f of x is, when we do in 2 dimensions, it's differentiable at x naught. If we can show that the limit is delta x goes to 0, f of x naught plus delta x minus f of x naught, all of that divided by delta x exists. And y was f of x, of course. It showed a couple things. It showed that the tangent line had a defined slope. It wasn't vertical. It showed the function was continuous at x naught, and it could be closely approximated by a line near x naught. We would say f of x equaled f of x naught plus f prime of x naught times delta x. I don't know if you all remember that. Delta x. We're going to scale that up to multivariable functions, okay? So what we want to do is we want the same thing. So we're going to have z as a function of f of x, y. We want the tangent plane to be defined, so not vertical. We want continuity, this time at x naught, y naught. And we want values of f of x, y near x naught, y naught to be able to be approximated by some linear functions. So that's our objective. I do want you to recall that we saw in the last section, partial derivatives, their existence was not enough to show continuity. So let's take a look at what happens in 2D so we can scale upwards. So we have some curve right here. This is y equals f of x. And we got a point at x naught right here. And the tangent line is like that. So our dx is like this. Our dy like that is like that. The actual change in y is delta y. It's the full thing. So there is a little bit of an error between delta y and dy. And I suspect I don't have the right tangent line because that error looks pretty big compared to dy. It should. But I did. I'm trying to make it visible. And then we had df dx or dy dx. We know that as f prime. We're doing it at x naught. And that was approximately the change in f of the change in x. And so we had delta f was approximately f prime of x naught times delta x. Like these are values that the delta sign means increment of. So an increment of f is approximately f prime of x naught times delta x, and that's near x naught. So this is good for small values of delta x. So delta f and f prime of x naught times delta x, they are close enough that the magnitude of delta x is much bigger than that. So like this is the error. If we subtract the full value, delta y or delta f is another way for it. If we subtract that dy times delta x or the f prime of x naught times delta x, this is our error right there. We can compare that to delta x, and we want it to be a lot smaller than delta x. So let's take a look at that. We've got the limit as delta x goes to 0 of our increment of f minus that approximation, that f prime of x naught delta x. We divide by x. We break it out into 2 pieces. And we replace what delta f means. It's f of x naught plus delta x minus f of x naught. And this gets broken up. We know this limit right here is f prime of x naught. That's the definition. So we have no delta x in here. It doesn't do anything. So f prime of x naught comes from there. This comes down. We show it equals 0 as delta x goes to 0. So it shows that the error, or delta y minus dy, it's a lot smaller than delta x. This allows us to do what we wanted to do, our approximations. Now let's just look at an example. We got y equals f of x, which is 3x squared. So let's look at dy and delta y. dy is 6x dx. Delta y is 3 times the quantity x plus delta x squared minus 3x squared. Remember, it's f of x naught plus delta x minus f of x naught. And so when we look at a point like 1, 3, and maybe a nearby value, like let's move over to 1.1 or something like that. Delta x is 0.1. We can see that dy, when we plug in our x and our dx, dy is 0.6. And delta y is 0.63. So delta y minus dy over delta x is 0.03 over 0.10. What is that, like? It's like 30% right there of the bottom. The top is 30% of the bottom. Well, that's a pretty big dx. Let's go with the smaller delta x. Let's make delta x 0.01. And we plug it in. Dy is going to become 0.06. Delta y, when we plug it in with 1 plus 0.01, and we square all that, we're going to get 0.0603. So now when we do delta y minus dy over delta x, we get 0.003 over 100. The top is 3% of the bottom now. And we see as delta x gets smaller, this error gets marginally smaller faster. Okay. So as delta x goes to 0, delta y minus delta or dy goes to 0 just a little bit faster. And so we'll extend this to multivariable functions in the next video. Peace.